Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is best practices for partial discharge measurements on medium voltage cables. My name is Michael Fleischer, and I'm the digital marketing analyst for Megger. I'll be acting as a moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Dr. Charles Nybeck, Substation Applications Engineer. To assist with the question and answer session, we will also have joining us Hein Puder, Product Manager for Testing and Diagnostics, and Jason Aaron, Applications Engineer. All right, let's go ahead and get started. Thank you for joining in today, Charles.
Thank you, Michael, for that introduction. And hello, everybody. Good morning, good evening, good afternoon, depending on where you are. Again, as Michael said, my name is Charles Nybeck. I'm a substation applications engineer, and today we'll be covering the best practices for partial discharge measurements on medium voltage cables. Starting first out with what we'll cover today in our presentation, we'll just start with a brief introduction into partial discharge, moving into the waveforms that are applicable for cable partial discharge testing. Then we'll move into the hardware setup for partial discharge testing, and then followed by the software execution, as well as some results analysis in that. And then we'll finalize it with a conclusion there. Right. So moving on to our introduction to partial discharge. So obviously the very first question when you're introducing partial discharge is exactly what is partial discharge, right? And here I have the technical definition of partial discharge, in which it states that it's a localized electrical discharge that only partially bridges the insulation between conductors, which can or cannot occur adjacent to a conductor. And the real takeaway from that is that we're partially bridging the insulation, so that's hence the partial discharge. Now, if left unattended, these partial discharges can worsen and lead to a complete breakdown, which would then be, kind of cause severe damage and could incur high costs as well, and cause unplanned outages. Now, this particular quote here or definition was taken from the IEC 6270 standard. You'll hear me talk about that a few times in this presentation or hear it mentioned. And the IEC 6270 standard is referred to as really the Bible of partial discharge testing. It's one of it's the first document, a horizontal document, in which there are several other documents that stem from it. But it's really the main partial discharge testing document there. Now, when we talk about partial discharges, they're typically present when the voltage stress across, and it doesn't have to be a void, but an insulation medium exceeds the dielectric strength of that insulating material. And whenever partial discharge happens, there are chemical and physical changes that take place, and these produce emissions that we can detect. We'll take a look at some of them. Some of the physical ones could be your apparent charge from the current pulse, which is that picocoulomb measurement. There could be electromagnetic pulses that you may decouple. Some chemical changes are ozone that's emitted or when partial discharge takes place. May not be quite as big of a deal for cable, but in terms of like rotating machines, ozone is extremely corrosive, so something that you really want to keep an eye on. And really, why we do partial discharge testing is it's one of the first indications of a deteriorating insulation system. And it allows you to take action if you're able to do testing or monitoring a partial discharge, take action before that defect starts to turn into a severe issue and maybe even, like I said, result in a breakdown or maybe even unplanned outage. When we talk about partial discharge, there's several different ways that it can manifest. Here we have just a simple example of a void discharge, in which we have our epoxy resin insulation and a void within that insulation. the dielectric strength within this void, because that void is filled with air, is likely going to be very much different from the epoxy resin, typically much lower than the epoxy resin. So you're going to have a concentrated electric field in this void area, and if it exceeds that dielectric strength of that void, you would have partial discharges taking place within here. And the problem with that is as the partial discharges are taking place, you may have carbon buildup, and that void may, those partial discharges may increase in strength and magnitude, and could again lead to a full breakdown between your two electrodes, your high voltage and your ground here. Another one that I even bold over here was surface discharges, and the reason I bolded that is because surface discharges are primarily the mode of discharge that we see with cables, and that's because they're layered surfaces, and those partial discharges typically take place on those surfaces, especially when we talk about splices and terminations and things of that nature, in which we typically see the partial discharge defects. And this is where you can actually see the partial discharge taking place, and that could be due to maybe a punctual effect, exceeding bend radius on cable, contaminants. There's several different cases in which that could happen. But you can actually see the discharge is taking place between your high voltage electrode and that XLPE surface there, which again is going to cause that carbon tracking and get worse over time, and could result in a breakdown there. Then finally, one is one that we're probably all familiar with, which is corona discharge. We've likely all either heard it and or seen it, in which there's a discharge in a gas medium between your ground and or your high voltage electrodes, if you exceed that dielectric strength there. So as you maybe, if you're doing some high voltage testing, you maybe start to hear some corona discharges, and maybe if you've done partial discharge testing, you may have seen some corona discharges if you had maybe, for instance, a termination that had like a live break or a NEMA lug at the end or something of that nature. Going into some important terms as I step through the presentation. One is the partial discharge inception voltage. And again, that's here I have the definition, and it's the voltage, the applied voltage at which repetitive partial discharges are first observed in your test object as you're gradually increasing from a lower voltage in which partial discharges were not taking place. So essentially, if you're doing a test, you start out at a very low voltage and you don't see any partial discharge, and you gradually increase during your test. And when you start to see repetitive partial discharge pulses, that's going to be your inception voltage. And conversely, your extinction voltage is going to be that applied voltage in which those repetitive partial discharges cease to occur or take place in that test object, as you're reducing now gradually from that inception voltage or that higher voltage where partial discharge is taking place, to again that voltage at which the partial discharges cease to occur. And that's going to be your extinction voltage. And it's important, these two are very important, and I'll talk about them a little bit later, because your inception voltage and extinction voltages are always going to be different, where extinction voltage is always going to be a little lower, as partial discharge is somewhat of a self-sustaining process. And again, I'll touch base on this a little later in the presentation. Next is apparent charge. So we may have heard this a lot. This is your picocoulomb measurement, and it's essentially the charge that when injected at the test terminal gives you that same reading on your measurement instrument that the partial discharge itself would give. And what that means is that you're not directly able to measure the partial discharge because it's taking place within your high voltage asset. So we're decoupling it at the terminal, and it gives you again that apparent charge or picocoulomb, sometimes nanocoulomb measurement there. And the final important term that I want to cover is voltage gradient. This is very important because, as I mentioned, specific to cable, most of the discharges that are going to take place are going to be those surface discharges. And surface discharges are extremely dependent upon the voltage gradient that's applied, the applied voltage gradient. And what that is the change in voltage with respect to time, or your dV/dt. And we'll take a look at, when we look at the various waveforms, of what I mean by that. But it's important to remember that it is strongly dependent upon the voltage gradient to ignite those partial discharges with surface discharge defects. Now, there's several different causes for partial discharge, and there's several different measurement techniques as well. As we mentioned earlier, partial discharge is typically overall caused by a dielectric stress. Now, this could be non-homogeneous distribution of the electric field. As we talked about earlier, this could be, due to the bubbles or in your solid or liquid insulation, localized stress because of punctual effects that we talked about, presence of moisture, water pockets, contaminants on the insulation surface, things of that nature, or just overall exceeding the dielectric strength of that insulating material. Now, as I mentioned, the partial discharge current pulses that are taking place in your high voltage apparatus can't be directly measured because that PD source is not accessible. So therefore, we have to use several different methods, or there are several different methods available to do partial discharge testing. And I've broken them into two different topics here. One is conventional and one is unconventional. For this purpose, or for the purpose of this presentation, we're going to cover the conventional method that's covered by that IEC 6270, or defined by that IEC 6270 standard, in which we're measuring that apparent charge or picocoulomb or nanocoulomb value. Now, there are unconventional methods that I'll just mention. Some are electromagnetic. So for instance, you may have heard of partial discharge detection on cable by using high frequency CTs to decouple that electromagnetic signal. Now, other methods are like acoustic detection that are typically used for location, maybe on GIS or transformer, optical methods, and then of course chemical methods. But again, we'll be covering the conventional method. So now that we've kind of gone over a brief introduction to partial discharge, I'd like to take a moment to look at the waveforms that can be used for cable partial discharge testing. So here we have three appropriate waveforms that can be used for partial discharge diagnosis. We're probably all familiar with the one on the left, that is our continuous sine wave. And there's various different applications, or I guess various different methods of using the continuous AC sine wave. And what I mean by that is, on the left, you can see we have our 0.1 hertz, which is our VLF frequency. At the bottom here, we have our a resonant frequency in which a resonant test set could be used. And then finally, we have our power frequency, 50 or 60 hertz, depending on where you are. Now, the second option that maybe not everyone is familiar with is damped AC. It's a method that's kind of more of a finite method that decays over time, a short period of time, over milliseconds. So this is kind of a blown out view, but if we look into it, you can actually see this AC, damped AC sine wave that's coming through and decaying over time. And I'll talk about this on the next slide, actually. The final one is our cosine rectangular here. The cosine rectangular is unique in the fact that it actually has two components to it. And what I mean by that is that the fundamental frequency is this 0.1 hertz, so that VLF frequency. So you still have that VLF in there. But upon your polarity reversal, and similar methods to your damped AC, you are actually creating a frequency, a resonant frequency, depending upon the inductance of the unit of your test set and the capacitance of your test cable. You'll come up with a frequency that's comparable or representative of power frequency. And that's the same way that the damped AC works as well. You have basically a DC power supply that charges up to your desired voltage, and then depending on the inductance of the unit and the capacitance of the cable, you come up with the frequency of that wave. Now, looking at them kind of a little bit more individually, here we have an example of the damped AC, so damped alternating current, in which, as I was talking about, you have a DC supply that charges up to your desired voltage, and then a solid state relay will typically close, and then based upon the inductance of your test instrument and the capacitance of your test object or your cable, you come up with a resonant frequency between that 20 and 500 hertz and this decaying AC wave. And this is really ideal because it not only is comparable to power frequency results, but it has its certain application. And what I mean by that is you can tell that it's more of a finite millisecond wave, as well as a decaying wave, in which most of your partial discharges are going to take place kind of in the first period where you have the higher voltage there. And what this does is this allows you to perform partial discharge diagnostics comparable to power frequency while not applying a constant load to the cable. So this would be ideal for performing maybe diagnostics, partial discharge diagnostics on service aged cable, or maybe a cable that you really don't want to cause stress on the insulation. So again, a very good tool for service age cable and performing partial discharge diagnostic measurements. Plus, you are able to kind of set your finite measurements in terms of setting your voltage and the number of excitations, and that'll make more sense whenever I go over the software functionality. Our other one that we kind of want to cover here for partial discharge testing, or that's mostly ideal for partial discharge testing, is our cosine rectangular waveform. And as I mentioned previously, you have your fundamental VLF 0.1 hertz, so you have that 5 seconds period, or a half period. And during your polarity reversal, you're again coming up with that resonant frequency that is representative and comparable to power frequency results. And so now you're able to perform a VLF test while performing partial discharge measurements during that polarity reversal that are comparable to power frequency results. And an ideal situation where you may want to use this is maybe the commissioning or acceptance testing of cable, or testing of new cable. So now you can stress the insulation, perform that VLF test, and actually also perform partial discharge testing at the same time. Here we have several different waveforms overlaid. In blue, we have our 60 hertz. In the orange, we have our VLF sine wave, a full period. So then you have 600 cycles on your 60 hertz. And then we have our damped AC in red. You can see just kind of the decaying wave shape. And then in black, we have our cosine rectangular. From this view, you can't really gain a lot. So let's take a look a little further in. So 20 cycles. And then if we zoom into 10 cycles, actually, we want to look at the individual waveforms. And we can see our 60 hertz in blue. And we can actually see our damped AC in red. So our damped AC, again, it charges, you close your relay, but depending on the capacitance and inductance, you get this resonant frequency that's very comparable to power frequency. And again, you can see as it goes on that it's decaying over time. But one thing to pay attention to is again, the voltage gradient here, that it's again very comparable to that power frequency. And as I mentioned earlier, it's very important to have that voltage gradient to get to ignite those surface discharges, or to get the appropriate voltage, inception voltages and extinction voltages. Because if you don't have that voltage gradient, for instance, on our sine wave here, our VLF sine wave, we can see a very low voltage gradient here. Very slow change in voltage with respect to time, right? So you can see the others change voltage rather quickly with respect to time, as our VLF sinus does not. So this may skew your inception voltage and extinction voltages, and may not be representative of when it actually goes back in service. Now, the other one I haven't spoken about is our cosine rectangular, where we have our fundamental VLF 0.1 hertz. But if we look at this polarity reversal, we can see how it actually follows that same frequency of our power frequency. So again, showing that it's comparable to power frequency, and that's where we would actually get our partial discharge measurement and perform our VLF testing during that fundamental 5 second half period there. So I think this is a strong image to actually show the change in voltage with respect to time. And again, I just kind of want to reiterate that really is an advantage when performing partial discharge testing on cable and layered surfaces there. This is kind of just a table that summarizes the different waveforms and their applications. So first we have our cosine rectangular, and it's ideal for VLF testing and partial discharge diagnostics. So for VLF testing, kind of outside of this, but FYI, cosine rectangular utilizes the power or the energy stored within the cable and allows for testing of longer cable if you're doing VLF testing. Now you can also, it's able to perform VLF testing and partial discharge diagnostics simultaneously by having that 0.1 hertz fundamental frequency, this here, and then having that polarity reversal that is close to that 50, 60 hertz or that power frequency. Now you have VLF sinus, which is a very common waveform. And really the recommendation is to use this for the tan delta diagnostics. And that's really because it's required to use the zero or the sine wave for tan delta diagnostics. But when performing partial discharge, as we mentioned earlier, you really have that low change in voltage with respect to time, which may skew your measurement results. Finally, we have the damped AC, which is ideal for our partial discharge diagnostics. And the reason being is it's a fast method of testing. It's very clear, and it's easy to identify your inception and extinction voltages. As I mentioned earlier, they're discrete measurements, and we'll take a look at that, what I mean by that. And you can step up in voltage in terms of maybe times your RMS voltage, and actually identify what your inception and extinction voltages are. And then also, same with cosine rectangular on the polarity reversal, the damped AC is going to be representative and close to that power frequency as well. So allows for comparable results there. Next I want to talk about some aspects to consider when setting up and performing a partial discharge test. And one is your power source, and that can be your input power quality. And what I mean by that is I've had an instance where I've performed partial discharge testing and I used an inverter, and whenever I was checking my background noise or my disturbance level, I was actually picking up those IGBT switching noises on my background noise. So you want to pay attention to the input power quality to your measurement instrument. Another is the output waveform for your application. So as we covered just in the previous section, if you're testing service aged cable, and it would be ideal to use your damped AC, again, because you're not applying a constant stress to the cable, and you're able to perform the partial discharge diagnostics. Now, if you're doing commissioning or acceptance testing, it would maybe more ideal to do cosine rectangular, in which you can perform your VLF test, stress that insulation, that new insulation, and also perform your partial discharge test during the polarity reversal, with both of those methods, again, being comparable to power frequency. Next is to pay attention to proper grounding. This is very important. This is not only for your safety, the instrument safety, but also for the quality of measurement, to be honest. If you have maybe loops in your grounding or poor grounding, then it's going to affect your measurement, and it could lead to some erroneous results or difficulty in finding the partial discharge. So proper grounding is a big one there. Next is our connection to our termination. So there's several different ways to connect the terminations, and there's several different types of terminations. So as I mentioned earlier, you may have a live break where you may have like a NEMA lug, and it may be ideal to use maybe corona rings on that and connect to that, because of the sharp edges that are on that NEMA lug that may cause corona discharge as you step up. Another instance is you'll see in a load break elbow here a solution that we came up with that was kind of custom to us, using a diagnostic kit where we used a corona ball and actually attached it to a bushing well insert, and we used that to insert into a load break elbow and it has an MC connector for our high voltage to connect directly onto. You also want to check for debris. You want to make sure that there's no debris on your test object, as we saw that contaminants or moisture can actually lead to partial discharges as well. Then calibration. This is likely this is going to be the most important thing to partial discharge testing. And what I mean by that is your calibration is really going to tell you what your quality of measurement is. I mean, can you see all the splices in your TDR? You know, how clean is it? Things of that nature. So if you have a really good calibration, chances are you're setting yourself up for a quality measurement. Next is the disturbance level, also called the background noise. And this is obviously important because if the background noise determines what you can see. And what I mean by that is if you have a background noise of 500 picocoulombs, let's say, you're not going to be able to see any defects lower than that because that's your noise floor. And then finally, determining your partial discharge inception voltage and extinction voltages. And I'm going to give some quick examples of why that's so important, because these are really, really important when you're doing offline testing. The first is the most ideal example. Your inception voltage, which is the voltage at which partial discharge starts to take place, is found to be above your operating voltage. And then as you're going down in voltage, your extinction voltage is also found to be above operating voltage. So now you have the confidence that even if you were to have a surge, a transient of some sort, that if partial discharge were to start taking place, once it settles back down to operating voltage, that partial discharge would cease to take place. The next is kind of the tricky one, which you may have inception voltage above operating and extinction voltage below operating. And what that means is whenever you do have that transient, you may incept that partial discharge, and once it settles back down to operating voltage, that partial discharge is going to continue to take place. And then of course, the worst case scenario is both your inception voltage and extinction voltages being below operating, which means you have partial discharge taking place all the time while that cable's in service. So just kind of 3 examples of why finding these values is so important. So now on to kind of showing you guys some of the best practices and in hardware setup and the software execution. Here we have an example or a picture of a junction box at our AVO training yard. All of these cables are de-energized. This is just a training yard here. But of course, when coming up to this, you would want to go ahead and test, make sure that it's safe, that it's off, and that you can handle it. So again, safety is always number 1. So you want to make sure to make sure that this would be de-energized before working on it. Afterward, we're going to inspect and see what's going to be our test object, right? So if we look, we can see we have several different test runs here for various different tests. So anywhere from fault to tan delta, VLF, and partial discharge. We're obviously talking about partial discharge today. So our run is going to be this 3D to 3G, and then the other end would be 3G to 3D. It's 950 feet, and again, for partial discharge, and has 4 splices in it. So we'll take a look at that again when we look at software, but just kind of want to show you guys what we're connecting to. Next would be, once we know our cable run and what we're going to test, and we've looked at our schematic, to identify the actual cable. And you can see them on the feed throughs here, the 3D, 3G, and 3G to 3D. So once we've identified that, we want to ensure that we have proper grounding. So looking inside the junction box, we can see that there's actually 2 ground rods that are driven in on either end. So those are driven in really well, and there's a copper braid that goes from one copper rod to the other, and then each of the concentrics come off and tie off to that copper braid. So we can ensure that we have nice solid grounding here. Once that we've inspected and we've ensured that we have a good ground, we can go ahead and back up our test system as close to our test object as possible. You may not always be able to get this close, but because you want to try to keep your connections as short as possible, so backing up as close as possible is always ideal. So here we have kind of the test van solution that's kind of your all-in-one. As you can see back here, you can do anything from your cable fault location to diagnostics. But obviously we're interested in doing partial discharge testing. But no matter what, you always want to pay attention, and your first connection should always be the ground. So we'll identify our ground reel, and then now we've already identified our ground rod, so we just bring out the reel and attach it to our ground rod and ensure that we have a solid connection there. Once we ensure that we have a solid ground connection, we can move forward with the rest of the connections that are necessary. Our high voltage and our communications, and this is just simply power to the actual van itself. Showing you the actual connections afterward. So you got a nice clean closed van. You can see that we have our ground coming out and connected. You may ask yourself, why is this high voltage cable tied to this traffic cone here? And the reason being is we really don't want the ground to influence our high voltage measurement. So it's ideal to keep that high voltage cable elevated and air insulated, so that way you don't have any influence of ground. And you notice that our ground connection also is not near our high voltage connection, so that way we're keeping some good distance there as well. And you can see the nice short connections to our PD coupler. So this is our capacitive PD coupler, and then to our device under test, which is our cable that we've already looked at. Now, another solution you may experience if you don't have the all-in-one cable van would be a portable test set, right? And this is kind of probably going to be more common. And here I did the exact same thing. I backed the van up. You can obviously tell I'm in a different van here, and where I have the portable test set connected and set up. I left it in the van so that way I don't even have to lift and carry anything out. The van kind of shields and gives me shade so I can read the computer screen, and again, keeping those connections short as possible. Again, same as the first instance, our very first thing that we want to do is connect our grounds. In this case, because we have a kind of a base set and a booster set here for our cosine rectangular and damped AC capabilities, we have our interconnecting grounds. We want to make sure that we have a single point ground for safety reasons, and again, for the instrument and for quality measurement. You don't want any ground loops or loops that would create an antenna effect. The second ground is from this communications box here, and we can see those grounds coming out nice and straight, and then coming in to our grounding point within our junction box, right? So again, that's going to be our first, very first connection that we're going to make. This is just another image. You can see the grounds nice and straight and come out, and again in there. This is an extension cable, I promise. I know it's cold, but that's not a ground. So other than that, we have the rest of our connections. So we have our high voltage cable, which again, I use my trusty traffic cone to keep it air insulated and off the ground. In this case, you're going to notice this, which is what's called a support capacitor. This is just used in some instances. You may go out to test, and then you try to perform your test, and it says capacitance too low, can't charge the cable. So in that case, you may need to add this support capacitor to add capacitance to the circuit. So we can see, and you want to make sure to place this before our coupling unit. So again, then we have from our high voltage, our detection unit, our high voltage cable out to our support capacitor, to our coupler, and then again to our cable that's under test. So again, a pretty straightforward connection. And that communication box that I was talking about, you can see this cable here comes to the coupler itself as well. Actually, on this side, you can see it kind of wrapping around. This is kind of the bird's eye view. Actually, you can see I'm in the van right next to the test set. I always like to be able to keep an eye on my test circuit. So while I'm performing the measurements, I can keep an eye on anything everything in case I need to make any actions or corrective actions. So now that we've talked about kind of the test setup of the two different, the van solution and the portable solution, another thing I wanted to talk about is the termination, right? And when I was doing this testing, it was in July or such, and so it gets extremely hot here in Texas. The grass dies, and Texas is relatively flat, so the wind blows, and that grass sometimes gets caught up in this silicone grease. So whenever you are examining, visually examining your terminations, as we talked about earlier, we want to make sure that it's contaminant free, as that could cause partial discharges, and again, could skew our inception and extinction voltage measurements. So the proper thing to do in this case would be to clean it with a lint-free towel and make sure that it's nice and debris-free, and then re-lubricate it with some more of their silicone grease. Next is how to connect into your load break elbow, or how you're going to connect your high voltage cable to that load break elbow, or your to test that cable. And this is kind of that custom solution that we had talked about, where we took this bushing well insert, where we would insert here into the elbow, and then this is going to be our test point, where we have a corona ball and an MC connector that allows us to just simply connect the high voltage cable on. So you can see several different aspects of it here. And we've found in using this that we've been able to go higher in our test voltage without experiencing any partial discharges at our terminations. This is an example or a picture of it actually connected. So as I mentioned, you have your load break elbow, the bushing well insert, the corona ball that's screwed in, and then as well as the MC connector, where our high voltage connection is easily connected. Okay, so now that we've gone over the hardware setup, I'd like to take some time and cover the software execution as well as the results analysis. So just kind of wanted to cover this again. Of course, we know the junction box, right? But I wanted to just look at the run again and remind you guys that we do have a 950-foot run, and that we have 4 splices that look about equidistant apart. Now this is important because the first thing we're going to do in our software is build the cable. So we have a schematic of the cable. Now we need to translate it into the software. So we'll go to our cable editor, and we can see at the very top that we have our header information. So you have your cable number. I just put the AVO yard, our training yard. The RMS voltage, this is very important because as you go into the test mode, it's going to use that to determine your test voltages. And we'll look at that as you go to the high voltage measurement. If you do measurement in terms of multiples of your U0, which is your RMS voltage, you want to make sure that that's accurate, because if it's not, then your applied test voltage won't be accurate either. So pay special attention that this is your RMS voltage. Here we have the 2 ends of our cable. So our D and our G ends. I'm in Dallas. It's manufactured by 3M. They're air insulated and cold shrink. So obviously you can see you can change the type of insulation and termination, and clarify some of just the header information. You even have the ability to put in a picture if I wanted to. So you could browse and actually put in a picture, and it would look good in the reporting for you. At the bottom, you actually see my cable already built. I had already built it before, but if we wanted to build it, what we would do is go to the Sections tab here. And you can come to Add. And Add allows you to add any type of section of a cable you want. So you can specify the length, the type of cable. Is it XLPE like here? Is it EPR? Is it PILC? There's several different things to choose from, or options to choose from. Notice that the length is in meters, so I just simply converted 950 feet to meters, which is about 290 meters. And I know that the joints are equidistant. So I just divided it by the 5 stretches of cable here and get 58 meters apiece. And you can see that I was able to put my 58 meters of XLPE and then specify what type of joint I had that's seen visually here. And you want to pay attention, special attention to that, because you want to see if that partial discharges line up with your splices, so that way you would know exactly, where in the manhole or where along the cable you need to go to identify that partial discharge. So you can see that I have 4 cold shrinks, which are our joints or our splices that are in the cable, followed by the 5 stretches of cable that make up our entire 950 feet here, or 290 meters, as you can see. So now we have the cable built, and we can go ahead and save it. Next is going to be our new measurement task. So now we have to actually choose what cable we're going to test. You can see I selected the AVO yard, which is the cable that we just built. Now look at, notice there is a library in here, so you can have several different cables that you've built and have them saved in here. And one unique thing, or one, thing that I really like about this is if you test a cable and you go back to test it later, maybe for whatever reason, you can always access that build again and access that previous measurement as well. So even if you were out performing a test, let's say 5 years later, you could then pull up the previous data and even do a comparison at that point in the field even. So that data is always saved, as well as those previous cable builds, unless deleted. So we're going to select our AVO yard cable build, and you can see that this kind of wheel here actually guides me now that I've selected my cable, and you can see it selected. Verify that everything is correct. We can move forward to the next step, which is our calibration, which is illuminated here in orange. So as I mentioned previously, calibration is likely the most important part of performing a partial discharge measurement. You want to make sure that you'll have are connected as close to the conductor and as close up on the concentric neutral as possible. You can see my negative here on the concentric neutral, and I have a space right on top of my corona ball to do my partial discharge measurement, or calibration here. Next is to determine the magnitude of calibration. You can see I'm injecting 1 nanocoulomb. The reason I choose 1 nanocoulomb is because you want to calibrate to a magnitude of similar to what you expect to see in partial discharge. And what I mean by that is, in cable, partial discharges are typically some hundreds of picocoulombs and maybe in the order of nanocoulombs. So 1 nanocoulomb is kind of really the go-to for on-site testing, unless you experience higher noise, and I'll kind of cover that in the instances forward. But 1 nanocoulomb is typical for that. I mean, if you were doing maybe rotating machines, it may be 5 or 10 nanocoulombs because those discharges are higher. So it just depends on your type of asset. So we've clicked our calibration. Now that we have our calibrator connected, the first thing we want to do when we're in our calibration is going to be that verify that we have all of our settings correct. We have the correct phase selected. Our bandwidth is typically always going to be high. It's ready for us to calibrate. Our length is correct, and our charge is correct because we're injecting 1 nanocoulomb. So we're ready to go. So we go ahead and hit start. We can see nice, clear charge pulses being injected. This blue kind of fuzz on the bottom is our noise floor. So even before, and we're going to determine what that is actually moving forward. That's our disturbance level, right? But we can already tell that we have a strong signal to noise ratio here, because this is our signal, that are our 1 nanocoulomb injected signal. Also, we want to verify that we have a nice clean TDR pulse, where we have a strong initial reflection. We have a splice here, our first splice, our second splice, our third splice, our fourth splice, and then our end, the end of the cable, our end reflection. So we can go ahead and verify that this is a solid calibration. Now, in this instance, what I did is I took the grounds and I looped them as I said I shouldn't previously. So I went against one of my best practices. And what I also did is I moved and kind of poorly connected the calibrator leads. And you can see that with the exact same settings of 1 nanocoulomb and while injecting 1 nanocoulomb, and then still on phase 1, that we were getting a poor signal to noise ratio with erratic charge signals being injected, and our TDR pulse is nothing, right? Could not be usable. Now, in cases like this where this may be real noise, I simulated this by doing the don'ts again, by coiling my grounds, which you shouldn't do, and then poorly connecting my calibrator, which again, you want to make sure you have a nice connection close to the conductor and close to you up on your concentric. But if this were actual background noise, you could increase the injection charge. So I went up to 10 nanocoulombs in this case, and you can see kind of a better signal to noise ratio and a decent TDR pulse at this point. Now I went ahead and moved forward with the first calibration, just our 1 nanocoulomb. And now you can see I saved the calibration, and the software is now telling me we're ready for our disturbance level and high voltage measurement. So the first thing again we want to do is make sure that our settings are correct, where our phase is correct and our Q range is correct. We injected 1 nanocoulomb, so let's go ahead and keep it at 1 nanocoulomb at the moment. We'll see what happens whenever we change that. We hit start and we can see that we get our actual max charge, and you can see it down here as well, nice and soft and smooth there, where we have a max charge of 50 picocoulombs. So what that's saying is our background noise is 50 picocoulombs, and therefore we should be able to detect any partial discharges that are above 50 picocoulomb in magnitude. Now, if you change your Q range, for instance, here we can see 100 PC, which may be ideal for maybe a shielded room or a laboratory environment. It looks like our max charge is down to 6 PC, and you may say, well, that's great, you know, that's a lower noise floor, but we're limiting what we can see in terms of those higher discharges. So if you were to have discharges at a higher discharge, you're limiting it, kind of like using an oscilloscope, you're changing the range down to a smaller range. So if you have a higher discharge, it'll likely exceed that 100 PC range, and you would have to change it back to the 1 nanocoulomb. And on the opposite end, I changed it to 10 nanocoulombs here, and you can see our background noise increased to 379 picocoulombs at this point. And keep that in mind, because whenever we actually find our defect, we'll notice that actually that defect is going to be flagged at being lower than that 379 picocoulomb, which means that we would have had to go higher in voltage, and it would have skewed our partial discharge inception and extinction voltages. So again, we want to be sure that we have the correct Q range whenever we're setting our disturbance level in accordance to the range that we calibrated in. Next is to move over to the high voltage measurement. So I've saved my disturbance level at that 50 or 47 PC magnitude, and I moved over to the high voltage measurement at this point. Next is to determine what test mode am I going to use. Because I know there's a defect in one of these splices, I don't really want to VLF it. We have runs that are meant for VLF, so I don't want to use the cosine rectangular. This is like your service age cable. So I want to use a damped AC method. So for this example, we're going to use damped AC negative. So we move forward, and I just started my measurement. Again, we want to start at a low voltage, so I started at 0.3 times our RMS voltage, and I did multiple excitations. And I did this, if you look at the IEEE standard for damped AC testing, they recommend to step up in voltage and to have multiple shots or excitations. And what that means is you can see your damped AC wave here, and it's going to shoot that out 5 times, or it's going to shoot this wave out 5 times. but it's going to be discrete and magnet and time. So again, we're not constantly stressing that cable, and we're able to find partial discharges. And we'll look at that later, an example of that. This gray box kind of shows you the first period here of the applied voltage wave and the partial discharges taking place, which we can see the max charge at the top left is only 47 picocoulombs, and therefore still just background noise. You can see the frequency is 416 hertz, and again, that's dependent upon the inductance of the instrument as well as the capacitance of the cable under test. Next, I just stepped up to 0.5. Not much change. Our max discharge is still 50 picocoulombs. I kind of added you can see I added the cable build here, and these dotted lines actually line up with the splices. So what we're going to do is wait for the algorithm to flag that partial discharge and determine the distance. So at 0.5, I stepped up to 0.7. Again, still just background noise at this point. So time to go up higher in voltage, right? So now I'm at 0.9, and still we're just getting our background noise. So we want to go ahead. One measurement you always want to get is 1 times your RMS, just because it's just a nice clean measurement to have. You saw I was stepping up by 0.2, but I always like to get that 1 just for your reporting purposes, but still just background noise. Finally, we went up to 1.2. I'm still doing our 5 excitations per voltage step, but now we can see our charge went up just slightly, but to 63. So I stepped up one more time, and now we have a max charge of 257, and we have partial discharge flagged on our cable as well. So, and you can see that partial discharge right here is that 257 picocoulomb discharge. And again, if we remembered, if we were in that 10 nanocoulomb range over here, we may not have seen that because our noise floor was that 379 picocoulombs. So again, really, really important to keep that in mind. So once the measurement's finished running, you can see it's stopped now, we want to save our inception voltage. So we now have those repetitive partial discharges as we gradually stepped up in voltage. So now we want to save that as our inception voltage. And you can see that the PD was flagged at 177 meters, which is just 2 meters away from the splice, giving us a strong indication of that partial discharge taking place in that third splice there. Once we have inception voltage, we want to go back down in voltage and find our extinction voltage. As we mentioned earlier, the 2 most important parts of your actual measurement here. So I stepped back down to 1.2 and did my 5 excitations, and I changed, if you notice, from the view from the discharges and my applied voltage to what's called localization. And the reason I did this is I like to keep an eye on this while going down in voltage, because it'll actually tell you where that partial discharge is flagged at taking place. It's at that 177 meter mark, which is telling me that at 1.2 times the RMS voltage, I'm still getting partial discharges. So you got to step back down. So now at 1.1, I see on my very first shot, there's 4 remaining, but on my very first shot, I have no localization. So you can see that the software is telling me it's not finding any more partial discharges. I let the software finish. All 5 shots are done, and no partial discharge was localized. So now I can go ahead and move and set and save my partial discharge extinction voltage. And now in this case, we have our inception voltage at 1.4 times the RMS voltage, and our extinction voltage at 1.1 times our RMS voltage. So I would say that good case overall, kind of close on the extinction, but still a good cable overall. So, but we can see that we did identify the partial discharge and which splice it was in, and if we would be able to go over there and repair that splice, test again, and verify that the splice was repaired correctly, and those partial discharges would cease to take place there. So, in conclusion, partial discharge testing offers the ability to identify and locate issues before they result in a full breakdown in service, creating either catastrophic failure or an unplanned outage, which either way is going to be very costly. And for cable, the predominant mode of partial discharges are going to be your surface discharges, which are strongly dependent on that voltage gradient or that change in voltage with respect to time. And it's important to choose the appropriate test waveform, whether it's damped AC for that service age cable or cosine rectangular for maybe the newer cable, whether it be commissioning or acceptance testing. Finally, the test setup is extremely important to give you those optimal results. So you have to pay attention to your grounding, again, important for your safety, the instrument safety, as well as the quality of measurement. We saw what happened to the calibration when that happened. Proper lead and equipment placement. So again, you want to have that high voltage, air insulated. You want to have your equipment kind of as close as possible with short connections. You want to pay attention to terminations. Is there any debris on them? And how am I going to connect to this termination in a way that's going to allow me to step up in voltage and not experience maybe corona and make me think that there's something wrong with my termination. Then finally, calibration. As I mentioned before, probably one of the most important parts of partial discharge testing, as a good calibration is going to set you up for a good partial discharge measurement. And then disturbance level, as that's necessary to know because that's going to be the threshold in which you're able to measure. I mean, anything below, you will not be able to see anything below that disturbance or background level. And then when performing offline cable testing, it's crucial to determine your inception and extinction voltages, as I explained earlier, to determine the severity of that defect and whether or not you can kind of even grade, if you will, if you have multiple cables, which, a replacement program to determine which cables need to be replaced more soon. An overall partial discharge testing on medium voltage cables is an extremely powerful diagnostic tool and can be used in several different ways, as we talked about with damped AC or cosine rectangular, to find and find localized issues or defects within your cable. All right, well, thank you very much. And I think that we're ready for any questions.
Yep. So first off, thank you, Charles, for going through all of that with us today. At this time, the presentation portion of our webinar is officially concluded. We'll now take some time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the GoToWebinar control panel. For those of you that are leaving, when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there's a field where you can also request a quote or a demo on any Megger products. A copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars, as well as register for upcoming webinars on our website at us.megger.com/webinars, and register for our next webinar next Wednesday, November 10th, titled Directional Protection Fundamentals, presented by Abel Gonzalez. All right, let's get into the questions. The first one I will be directing to our panelist, Jason Aaron. Jason, can a person be injured if he approaches a cable which is in a partial discharge mode?
Okay, thank you for this question. So first we have to understand that whenever we're taking partial discharge measurements, that we have to pass a high voltage source through the cable to be able to get to the point where we're producing partial discharge to be able to measure it. So for that very reason, yes, there's dangerous touch potential at each end of the cable whenever we're taking these partial discharge measurements. So for those reasons, whenever we're doing this type of testing, we have to ensure that both ends of the cable are properly isolated. And that means both from any other source of ground that may impede the partial discharge measurements, but also from being able to be accessible by other individuals or workers that might be in the area. So to do this, we want to barricade off the area. You're going to want to post technicians at each end of the cable to make sure that they're properly guarded. We also want to make sure, as Charles mentioned, whenever we do our test setup, that the instrument is properly grounded, the cable is properly set up, and shielding is grounded. And again, that we make sure that we barricade off each end of the cable to make sure that someone can't inadvertently touch either end of the energized cable while we're taking the partial discharge measurements.
Thanks, Jason. Our next question I'm going to send over to our other panelist, Hein Puder. Hein, is PD testing non-destructive?
Yes, hello from my side. I first want to say thanks to Charles for the nice insight in the presentation he performed with regards to how to perform a PD test and where to pay attention to. And going to the question, which is a good one, is PD testing non-destructive? Non-destructive, this basically depends. So like Charles has mentioned, there are several wave shapes which you can apply on a cable. And what we normally recommend for new cables is that if it's a new cable, then you should apply the VLFCR wave shape or VLF wave shapes, because it needs to withstand the voltage. If you have aged cables, so could be a very old paper cable or could be maybe a water treat XLPE cable, then you certainly do not want to overstress the cable. And in that case, if you use VLFCR or resonance testing with overvoltages or VLF sine wave with overvoltages, you can damage the cable and you can have failures during testing or post-test failures. So for that, you need to be you need to take care of, or you need to know what you're doing. So if you're testing aged cables, we normally recommend the damped AC as if we short over voltage. If it's a new cable, then it should withstand the higher voltages. Then we normally recommend the VLFCR wave shape or resonance testing or 60 Hertz testing.
Thanks, Hein. Back over to Jason. What are the advantages and disadvantages of partial discharge versus VLF tan delta?
Okay, so whenever we talk about partial discharge testing in relation to other type of testing that we do to evaluate the insulation of a cable, when it comes to VLF or tan delta, all of these types of tests are done to give you a complete outlook of the quality of a cable. And all of these different techniques are going to show you, give you different information as far as what's going on with the insulation of the cable. Now, with VLF and tan delta testing, they're going to give you an evaluation of the quality of the cable, but the one thing that they lack is they're not going to give you a localized evaluation of the cable. So with partial discharge testing, what we're able to do is we're able to localize the bad spots within the insulation of the cable to be able to isolate it down to where the partial discharge is coming from. What this is going to allow us to do, whether we have partial discharge at the ends of the cables and the terminations, or whether we have it in the splices or even within air void or something where there's degradation within the insulation of the cable, we're going to be able to narrow that down to one particular section of the cable to be able to find it more quickly, to be able to evaluate how bad the partial discharge is in that section or spot in the cable, and then we'll be able to perform immediate action to be able to decide whether we need to repair, replace, or we can place that cable back in service depending on the evaluation of the partial discharge that is present at that point in the cable.
Thanks, Jason. Hein, we are using tan delta on a wide scale. Is the tan delta diagnosis a good tool to identify if PD diagnosis is needed?
Good. So if I understand the question correctly, then over here is meant that a utility is performing Tangens delta diagnostics, and based on the outcome of the Tangens delta diagnostics, they want to plan a PD diagnosis. Well, over there, like Jason already mentioned, it are two different measurement methods or measurement types. So if the Tangens delta is a global one, looking for the aging of the insulation, so normally for XLPE cables, it should be the water trees, or for paper cables, moisture content. And it is incapable of finding, or in most cases, it's incapable of finding partial discharges or defects in joints which discharge on a low level. So as it's an average of the entire cable, the Tangens delta diagnostics will not be capable of identifying that, and therefore it's not a tool to be used to plan your partial discharge diagnostics. So basically, it's both measurements are needed, where the Tangens delta diagnosis is only needed on aged cables, and on new cables, the PD diagnosis is recommended. So new cables, PD diagnosis; on aged cables, Tangens delta and PD diagnosis. Sorry.
All right, thanks, Hein. Back over to our presenter, Charles. Charles, how could I have low background noise before starting the PD test by software?
All right, good question. So there are ways. So first off is to determine what your background noise is. Now there are ways to lower that in terms of, you know, checking your ground connections and making sure that your high voltage connections are elevated and not close to ground, things of that nature. Now, in some cases, you know, there was a test that I did not too long ago, in which it was in the switchgear and the surrounding switchgear were live. Now there's the background noise in that case was relatively high. In fact, I think it was about around a nanocoulomb or a little higher. And there's not really much you can do in those situations, as you're just subject to the surrounding, you know, noise pollution there. So the most you can do is take those precautions to make sure that your test setup is optimal. And outside of that, you're kind of left at the mercy of what's being polluted around you in terms of other high voltage assets or high frequency disturbances as well.
Thanks, Charles. Over to Hein. How do we determine if the high voltage cable itself is free of partial discharge or not?
That is a good question. So nowadays, most cables which are installed are polymer insulated cables, so mainly XLPE. And those cables should be pre-tested at the manufacturer already. So if those cables are installed, then the main issues we identify, so I would say 90% or probably 99% of the cases, the problems will be in the accessories because they are man-made and mistakes can be made. Still, there is a chance that there is PD in the cable itself because of bad laying quality. So if they damage the outer jacket and also damage the outer semiconductive layer, then there will be PDs, and those partial discharges will not be as high as PD in a joint, but they will be higher than 20 or 50 picocoulombs. So what we have seen in the fields is that those levels are 100 picocoulomb, 150 picocoulomb, and you can still identify them with the offline test in the field. With paper cables, it's completely different. Over there, they are not designed to be PD free. So if there is PD within the insulation, it can be recognized and also localized. And over there, the PD magnitude normally starts at 500 picocoulomb, and within the paper layers can even go up to 20 nanocoulomb or even 50 nanocoulomb without being completely dangerous, depending on the type of paper cable you have.
Yeah. Back over to Charles. Is this an offline or online test? Up to what voltage levels of cables can this test be done?
So this specific example was for offline testing. Now, a typical method for online testing was that electromagnetic decoupling by the high frequency CT that I had mentioned kind of briefly. But what I was doing was an offline test, which uses that conventional method in which you're using an external high voltage supply to basically excite that partial discharge and take that measurement. Now, as far as up to what voltage in cables can this test be done, really, there is no limits. There are damped AC sets that can do testing on 230 kV cable. Obviously, as you go up in voltage and cable class, these systems will become larger. and they may become, trailer systems and maybe not van systems, correct, right? But you're really not limited by that voltage class, really. So you can do those EHV cables as well. So, but this particular case was offline testing. Not to say that you can't do online testing, but this was for offline testing, which offers a little bit more diagnostic capability.
Thanks, Charles. Our next question is over for Jason. Does partial discharge testing apply to EPR shielded power cable as well as XLPE?
So as we heard Hein talk about earlier in the follow-up to the last question that I answered, he mentioned testing on different types of cables, and partial discharge testing applies to all types of insulation mediums for cables, whether we have paper insulated lead cables, EPR cables, XLP, all of these types of cables. You can use partial discharge to evaluate these cables, and we want to use these partial discharge measurements. We can evaluate the quality of the workmanship or installation of a cable. We'll be able to also see if whenever a cable was installed, if a bend radius was exceeded, to be able to see if there's any type of separation within the cable that created a void that's creating partial discharge. But also, like Charles mentioned during his presentation, we can use partial discharge measurements for maintenance purposes to evaluate the service age cables. But as far as the question goes, this method can be applied to all types of cable insulation mediums.
All right, thanks, Jason. Charles, what test sets were used in this example?
Okay, so yeah, sure, happy to answer that. There's two different sets. One was our Centrix van system, which is the van solution that I had showed, where everything was all in one, in which you can have anything from all your cable fault locations, such as ICE method, ARM method, all sorts of testing in that sense. So all of your CFL capability, as well as T&D, and including doing VLF testing, tan delta, and partial discharge. So that's kind of your all-in-one solution for cable testing and diagnostics. Now the other one I had was in the back of the van, where I was doing testing, just standing in the back of the van, and that was the TDM 4540, which is kind of a unique portable cable test set that's capable of performing DC testing, sheath testing, as well as VLF, tan delta, and partial discharge testing. And that instrument, actually, that TDM 45, is capable of doing, your sinus VLF, damped AC, and cosine rectangular waveforms. So both ideal for doing partial discharge testing as well as other diagnostics for cables.
All right, thanks, Charles. The next question is going over to Hein. Is there a limit for declaring a PD is bad or okay?
Over here, let me start with standards. So if you look to PD, there is a standard how to describe or how to measure PD and what failures you can detect and what inception and extinction fault is, but there is no standard yet which gives any trending limits for on-site field testing for PD diagnostics. So I know that the IEEE 400.3 is now getting revised, and they will put in a limit for PD testing on XLPE cables. And over there, they will focus on the extinction voltage. And if it's, depending if you have a load break or a normal elbow, then the extinction voltage level should be higher than 1.3 or 1.5 U0s. Over there will be limits coming for new accessories. But for aged cables, it's all experience from manufacturers, from utilities, which are summarized in tables, which can be used for a starting point, and then the customer itself should build up his own database. But normally, looking to XLPE cables again, if everything is PD-free up to operating voltage, it's a good sign. If there are discharges at operating voltage, there's always something burning within your cable, so the risk is higher. And then it all comes to the importance of the cable. So is it the cable within an oil refinery? Then you want to have no risk. Then you want to replace that defective part. If it is just a simple cable going to some houses, then if it then fails, then it doesn't really matter. So over there you can say, okay, that's a cable with less importance. So over there, those PDs are still okay. I will check after 3 years and maybe then decide to remove or not to remove. No? With paper cables, it's completely different. So as I already mentioned, paper cables are not designed to be PD-free. And over here, you really need to look to the concentrated discharges. So if there is really concentrated PD within the insulation of high concentrations or high density, then some action need to be taken. But looking only to levels over there will not be possible. So there are more things where you need to pay attention to, like inception, extinction, intensity, rise of PD. So there are some guidelines which we supply, but it's difficult to explain in such a webinar. No?
Thanks, Hein. Over to Charles. You said the partial discharge level is around 1 nanocoulomb. How does one company claim they can test down to 5 picocoulombs?
That's a that's a really good question, and I think I know where this one's coming from. So when I said around 1 nanocoulomb, I meant that's the discharge that you can expect. As Hein was mentioning earlier, it depends on the defect, it depends on the cable. You know, PILC is obviously going to be much higher and several nanocoulombs. But if you're doing, you know, XLPE or EPR, you may expect defects more in the hundreds of picocoulombs and such. Now, if we're talking about testing down to 5 picocoulombs, I'd like to take a, you know, if we go back to my example that I had where I changed my Q range, and maybe if I had calibrated to 100 picocoulomb and changed my Q range on my software to 100 picocoulomb, if you noticed, my background noise was only 6 picocoulombs. So I could have found any defect that was anything at 6 picocoulombs. So that is a claim, sure, but if you're out in the field, then that's not, you're going to have some difficulties with that background noise. So it kind of depends on the situation. If you're testing in a low noise environment, for instance, if you were in a factory or a laboratory environment, then I would have calibrated it at a lower level and I would have been able to find PD at much of a lower level. But because I'm out in the field and I'm subject to that noise and the field environments, I want to kind of follow that 1 nanocoulomb rule. As you saw that partial discharge that we saw that take place, the inception voltage was right at about 250 picocoulombs. So I would say that it's possible to measure down to 5 picocoulomb, but it's not, I mean, in the field, it's not going to be very ideal or very applicable. I don't know. Hein, do you have anything else on that? I think that.
Yeah, so the 5 picocoulomb is basically the factory standard. So you must see it like that. If a cable is produced, then the manufacturer should do a PD diagnosis on each cable drum to prove that the cross-linking process, that there are no particles, that there are no microvoids in the insulation over there, it needs to have the level of 5 picocoulomb because those levels are really low. As those cable drums are PD tested and then going into the field, those levels of discharges we will not see in the field. So if there is a damage of the outer jacket, as already mentioned before, then the PD level will be in the range of 100, 200, or 300 picocoulomb. If there are problems in the accessories, then the discharges can be up to several nanocoulomb height. So the 5 picocoulomb accuracy in the field is in most cases not possible, but also not needed. Yeah? And the reasons being explained already. No?
All right, excellent. Thanks, guys. Our next question, while I have you here, Hein, is for you. Does that small corona ball help mitigate the effects of the sharp edges and corners of the nut above the ball?
Yeah, it depends on how high you go in voltage. So that was quite a small corona ball. So this was a 15 kV rated cable. So if you go to 2U0, it's what is it, 17 kV RMS, then it will probably still be okay. If you would use the same corona ball on a 25 kV rated cable, and if you go then already to what is it, 26 kV RMS, then you will probably already have corona. So then you need to have a bigger ball. Yeah? So over there, you need to check. Yeah? So if you have sharp points, they are getting shielded by the corona ball, or you can also use other corona rings, which you can produce by yourself or which you can buy as well to get at PD3. But corona can also be easily being recognized during the PD testing itself. So it has a specific PRPD pattern. So if you do your PD measurement and then focus on the partial discharges in your termination and you see that the PD is at the voltage maximum, then you know, aha, corona, connection issue, so not a problem. I can continue testing and discard those discharges at my termination.
Thanks, Hein. Over to Jason. What can be done if the cable is available for PD testing, whereas the other end remains connected to the gear but still isolated?
Okay, so when we're taking partial discharge measurements on a cable, it's important that that we're able to isolate both ends and air insulate each end of the cable. I understand that there's situations where it may be difficult to isolate a cable from a piece of equipment, but you have to understand that if the cable is not properly isolated, that's going to bring to the table its own set of challenges. And not only are there going to be more alternate paths to produce partial discharge, it's going to influence the partial discharge measurements that you're getting, but also it's going to be extremely difficult to be able to have repeatable measurements whenever you're doing future testing on that cable. And being able to do trending with your partial discharge measurements is also another valuable tool whenever we talk about being able to evaluate a cable over its lifetime as you do repeated partial discharge measurements. So for those reasons, it's extremely important to go that extra step and put the effort into isolating both ends of the cable. And like I said earlier, I understand that in a lot of cases it is very difficult to do that. However, to be able to accommodate this testing, it's extremely important that you do that.
Thanks, Jason. Over to Charles. Why is offline testing better than online testing?
So I wouldn't say better. I would say that they each have their advantages and disadvantages. If you have an online testing method, then I mean, obviously, then you don't have to wait for an outage. You can have you can have a more, I guess, the interval between test times could be less. I don't know what word I was looking for there, but anyway. So I mean, and then if you have a monitoring system, obviously you can set thresholds. You can always monitor that that device. So I mean, there's advantages and disadvantages to each. Now, offline testing, the particular advantage for cable testing offline is the fact that you can actually determine that inception and extinction voltage. That's the real advantage to doing offline testing with cable. As I mentioned, the importance of those two earlier, your inception voltage and extinction voltage are extremely important, because if you just know if you have partial discharge, you don't know if you, I mean, I gave those three instances. Your inception voltage could be higher, but your extinction voltage could be lower than your operating rate. So it's important to know those. So that way, again, you can determine and kind of grade the severity of the degradation in your cable insulation and kind of help to determine what cables need to be replaced at what time. So I wouldn't necessarily say better, though it does offer the strong advantage of being able to determine your inception and extinction voltages. But there are also, you know, some certain advantages to doing online testing and online monitoring, of course.
All right, thanks, Charles. Over to Hein. Is tan delta test as applicable to high voltage cables as it is to medium voltage cables?
If we look to the IEEE 400.2, over there are tables for Tangens delta in it, and they are mainly only focused on experiences gathered with 15 kV and 25 kV rated cables. A 35 kV class can be, for those tables can be used as well, but if you go higher in voltages, those tables have almost no meaning anymore. If you go into the high voltage cables, so 69 kV or 132 and higher, over there, Tangens delta measurements are in some cases possible, but there is absolutely no experience in the market with what is good, what is bad. So the only thing which you can do is compare phases with each other to look for some phase differences and then have the identification of a local defect instead of looking to the aging. So Tangens delta for high voltage cables as a detection of the aging, I would say for the time being not possible or no information available, and it's also not known if it can be detected using a Tangens delta measurement.
Thank you, Hein. Charles, how high do you go for test voltage to determine a good cable?
So what I did in this example is I followed the IEEE 400.4, which is basically a guide for doing damped AC testing on cable that is power cable rated 5 kV and above. And in that, it prescribes in stepping up in voltage up to 1.7 times your RMS voltage. So I would go ahead and go with that. I mean, sometimes you can go ahead and go up to 2 times your RMS voltage, but for that particular standard and following the damped AC IEEE standard, it would be 1.7 times your operating.
Thanks, Charles. Hein, is such a claim of 5 picocoulombs in the field in compliance with what you explained about IEEE 6270?
The IEC 6270 is a standard which talks about or which shows how to perform PD measurements, and over there no trending or no picocoulomb measurements, picocoulomb values are mentioned in there. So it's only how to perform a measurement, where to pay attention to, how to perform a calibration, how PD pulses look like, etc., etc. So the 5 picocoulomb is not mentioned in the IEC 6270. No, that's purely in the component or in the cable standard itself, or in the component standards for type testing or routine testing on those cable drums. No?
Thank you, Hein. Over to Jason. When doing offline testing, we would remove the cable with termination from the switchgear bus. Does this loose end contribute to corona problems, especially if the cable termination has the loose strands protruding from the termination?
Okay, so this is a good question about the setup whenever we're taking partial discharge measurements. And it's important to understand that whenever we connect to a cable and we set it up to do partial discharge measurements, we need to have PD-free connections to be able to accommodate the test, because the sources of partial discharge that we want to find whenever we're doing doing these tests, we want to make sure that they're valid. So To do that, whenever we set up on a cable, you're going to want to make sure that you have the proper corona balls for like a NEMA lug end to install to be able to make that a PD-free connection. Also for if you have load break elbows at the ends of each cable, you're going to want to insert a bushing insert into the load break elbow at the end that you're not testing, but you're also going to need an adapter on the end that you are testing to be able to connect that voltage source to the cable. Also, if you're testing a cable that has T-bodies or dead, also known as dead breaks on each end of the cable, then you're going to need the proper adapters to be able to do that as well. So the other part of this question that it asks about is if you have loose strands protruding from the terminations. Now, what this is going to do is it's actually going to promote partial discharge, and it's going to give you negative test results whenever you're performing the testing, because like I said, it's going to promote partial discharge due to the sharp edges and that are created from those loose strands protruding from the termination. So whenever you're doing this type of testing, anything that you see like that has sharp edges of the connection that has, or if you have loose strands because the cable termination was installed incorrectly, you're going to want to address those prior to taking your partial discharge measurements, because like I said earlier, all that's going to do is it's going to show that you have partial discharge while you're doing your testing, and that's not the point of what we're trying to do. We're trying to actually find points of valid partial discharge. So it's very important that you're meticulous about the way that you set up the cable prior to performing these measurements.
Thanks, Jason. One more question over to Charles. How do you know when you should save PDIV and PDEV values when using a VLF-CR?
So it's a good question. I didn't get to cover that example. Obviously I only covered the damped AC example because I didn't, because of my test object. But when performing your VLF cosine rectangular, it's going to be very similar to your well, it depends. I mean, one is if you're going to step up in voltage, right, and find that inception voltage. So while performing your cosine rectangular test, you can change the voltage. It's not going to be in as discrete steps as damped AC, because it's going to be a continuous output. But you can increase your voltage and decrease the same way. So if you were to look for your inception and extinction voltages using your cosine rectangular wave shape, you could still start at a lower voltage, that 0.3 times U naught, similar to like I did, and let it run for a bit and step up. Because similar to like I did with damped AC, you saw I did 5 shots or 5 excitations. So you'd let your cosine rectangular run for a bit and then step up in voltage gradually, and then do the same until you had your inception voltage. Then you could step down and find your extinction voltage there as well. So it'd be a similar process.
All right, Charles, thanks. I think we've got one more question I can send over to Hein for now. For example, in TDM 4540, without any load connection on it, how do we know if the test set high voltage cable itself is free of partial discharge?
That's a practical question again. So it's quite simple to answer. So like if you still can look out at those images that Charles showed on how you connect the TDM to the PD coupler, then basically if you don't connect any high voltage cable from the PD coupler to the test object, you can simply energize the PD coupler, so you can calibrate the PD coupler and then simply check if your complete setup until the PD coupler is PD free. So you should basically see no partial discharges up to 40 kV or 45 kV, depending on what system you have. And if it's then PD free, you know that everything from system until the PD coupler is PD free. And the last cable from the PD coupler to the test object is an unshielded cable. And if it's a shielded cable, then you can also test its shielded cable by putting it from the PD coupler to the support capacitor. So there are ways to check your setup without being connected to a test object.
Thanks, Hein. It looks like that's all the time we have for our Q&A session. I see we've gone a little bit over our scheduled time here. So I apologize if we didn't get to your questions here today, but we will be working to follow up with you offline. As a reminder, a copy of this presentation, a certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending, though. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all for attending today, and I hope you all have a great week.